Today we're going to be graphing different rational functions than we did the other day. This time, instead of being in the form y equals a over x minus h plus k, we're going to have a linear factor over a linear factor, or a linear function over a linear function. And a lot of the things are done the same way, but there are a few key differences. First of all is the horizontal asymptote. The horizontal asymptote is going to be when cx plus d equals 0. And this is why the other day I said don't think of it always as a left shift, right shift when you're talking about this x minus h down here. We want to think about it as what value of x makes the denominator 0. Because in this case, cx plus d, you need to set that equal to 0. Now, if your c value is 1, then yes, it will look like functions we did the other day, but sometimes you might have a 2x plus 4 in the denominator, and you need to set that equal to 0. And your HA, your horizontal asymptote, is the ratio of the leading coefficients. In other words, the ratio of A, the number in front of x on the numerator, over C, the number in front of x in the denominator. Everything else is the same. You're still going to make a table. You're still going to put the horizontal asymptote in the middle of the table and plug in points. So let's look at this problem down here. All right, your vertical asymptote, yes, there's no number in front of that. So you could just say that this is going to be x equals positive 1. But think about it in this sense. What number minus 1 equals 0? Oh, that's a positive 1. Your horizontal asymptote, that's going to be y equals 4 over the invisible 1 in front. So just 4. And your range is y can't be 4. So then we're going to go over here and plot the horizontal asymptote, the vertical asymptote at x equals 1, and then we're going to make that table. And remember how I said the other day in the calculator, if you go to alpha y equals, you can type in the fraction. In these problems, it's going to become much more efficient to do that. So 4 times x, so 4 times, what did it do? 2, 3, 0, negative 1. 4 times 2, minus 2, and then in the denominator, you have 2 minus 1. One of the things that students often forget is to plug in the same value of x for both of them. We get 6. And then if we go back and do it again, change both of these x's to 3. We get 5. And if I do 0, if I plug in 0, I'm going to get 2, but I want to double check that just in case. Oops. It's 4 times 0 over 0 minus 1, 2. And if you plug in negative 1, negative 1 minus 1, and 4 times negative 1, we get positive 3. So then we can plot those points. Okay. So that is our graph. So it's very simple to graph these if you've been doing a good job of graphing the other ones. So I'm going to let you guys try this one. Pause the video if you need to. Go back and watch what we just did on that previous one. So go ahead and please try this. All right, so you can see here, this is what we got. When we graphed it, we made our table, plugged those in, and the asymptotes, domain, and range. So compare yours to mine. And then we can flip to the next page. On the next page, we have a 3D printer that describes what it does. It builds up layers by printing a layer above the previous one. A car company decides to make a small display model of its vehicles using a 3D printer. The printer costs $24,000. The material for each model costs $300. Write an equation that gives the average cost per model as a function of the number of models printed. So if we were just to print one model, that would be the $24,000 that it would cost plus $300. Now, if we were to do two models, it would be plus $600. If we were to do three models, plus $900, and so on. So that would be the cost to print 1, 2, 3, 4, 5 models, and so on. But if we wanted to find the average, we would divide by how many models we printed. So if we wanted to do like 3 models, okay, each model is $300, so $900 to print plus the $24,000 to make it, and we divide by 3 because we made 3 models. What if we made 4 models? Okay, 1,200 because 300 times 4 is 1,200, divided by 4 because we made 4 models. But we want to create an equation for any number. So each model was $300, and we multiply that by the number that we printed. And then we're also going to divide by the number we printed to get the average. So if we did 10 models, we would divide by 10. So this would be our function for the average cost per model. Now use the graph to estimate how many models must be printed for the average cost to fall to 700. Right here, 700 for the y value. The x value that goes with that is 60. So 60 models must be printed. And let us see what happens to the average cost as more are printed. Well, look at the graph. It gets closer and closer to a certain value. And that certain value is going to be $300. And that should make sense. If you look at the equation, the leading coefficient on the top is 300. The leading coefficient on the bottom is an invisible 1. Even though it's not written with a 300x first, it still would follow that rule. So the average cost would get closer to $300. So now let's look down below at a summary of the different forms we have. We have the general inverse variation form right here that had a vertical asymptote at x equals 0 and a horizontal asymptote at x equals 0. Then we had y equals a over x minus h plus k. Your vertical asymptote was at x equals h, and your horizontal asymptote is at y equals k. And then finally, we had your linear over linear rational function, where the vertical asymptote, you had to set the, you should have to set the denominator, not the numerator, equal to 0 and solve it. And then the horizontal asymptote is that ratio of the coefficients. All right, so I hope that this is starting to make more sense the more we build on this idea of graphing rational functions. So thanks for watching the video. Make sure to like it and subscribe.